morning. Welcome to the Colloquium series. Today, I have the pleasure to introduce our faculty member, new faculty member, Assistant Professor Dr. Baosen Zhang. Baosen works in the area of power systems, broadly defined. He covers from optimization to user-side utilities and data-driven side of the power systems. Baosen finished his PhD from Berkeley in 2013 with David Say, who is in networking and communication. Then he spent 1 year with Ram at Stanford, and I have many stories from USC and others telling me how we got to steal him instead of them trying to get him. He joined us in March 2015. He's a member of the energy group broadly defined, led by Dan Kirshen, who probably is here, hopefully, and also part of the Clean Energy Institute at the University of Washington, which is a multi-department inter and intra-campus center. Baosen received the Forbes 30 under 30 this year as one of the promising junior or emerging leaders in the field of energy. So today he is going to share with us his ideas and opportunities about where he is going to take us in the next 30 years or 40 years, but providing the building blocks as he presents his view on the topic. Baosen.
Thank you, Radha. So as you can tell from Radha's introduction, today I'll talk about power systems, and in particular, what's new in power systems, and the challenges and opportunities that these new devices, they bring to the power systems. So you look at the power systems, we often say power system is the most complex, the largest machine ever engineered. And it is accurate. Right? So if you look at this map gives you all the high voltage power lines in the US. And when you connect them out in a line, there's more than 450,000 miles of power lines in the US. So as a context, this is enough to go to the moon and come back. And this is just the high voltage lines. There's much, much more low voltage lines lying around too. And this large network connects about 20,000 large generators supplying more than 120 million loads. So it is very fair to say this system is very large and very complex. Right? So if you look at this list, what this list tells you is this is a list by the National Academy of Engineering, and they said power system is truly one of the greatest achievements in engineering. Right? So you have the list as the greatest achievement in 20th century, electrification or power is number 1. So it's a very good achievement. But as a graduate student or as a faculty, you look at this list, you should not be very happy that number 1 is electricity. Right? You look at this list, you should be a little bit concerned. Because the important number on this list is not the number 1. It's actually this number, so it's 20th century. Right? So we always finished, right? So this list tells us, hey, we already built these power systems. It works, the lights are on, you're recording this, right? Everything works. Why am I still talking about power system to you? Right? Shouldn't we try to do something new as academics? Right? So let's say, okay, let's try to do something new. So the people who came up with this list, National Academy, they came up with a new list. They said, let us look at forget about the 20th century, that already happened. Let us look at what will happen in the 21st century. What is new in the 21st century? Look at those challenges. Let's try to solve those challenges. So if you look at this new list, let's look at top row. Actually, every one of this top row has something to do with energy. Right? Look at the first one, making solar economical. This is still very much a power system problem. Also dealing with carbon and so on. So it seems like there's a little bit of mismatch here. Right? In the last list, we said we already accomplished. We built this very large, very complex power system. But this tells us power is still a big challenge going forward. And in this talk, I'll try to convey to you why this is the case. Why should we still care about power systems in the 21st century? And the large part of this talk will have something to do with solar. How do you put solar energy into the grid? But what may be surprising is that there is another challenge on this list we'll touch. And this is the surprising part is this. We'll also talk about advanced personalized learning. So what does power has to do with advanced personalized learning? Right? So by the end of this talk, I hope you understand that to make power system work in the future, in the 21st century, you have to bring in ideas from wide areas. And this is two examples. We have to understand how to make solar work, and we have to understand how to deal with people, how to deal with human beings. So why is power system changing? Well, if you look at the system, first of all, we have a lot of new devices, new resources coming to the system. Right? We have electric vehicles, we have solar, we have wind. So our old system is really not designed to deal with these new devices. Right? So these devices are actually causing quite a fundamental shift in the way we think about power, in the way we think about the system. Also, another thing that's new is we have a lot of information coming into the system. For example, this is a Nest thermostat, and you can think of that being a smart home. So as a consumer of power, you have a lot more control, you have a lot more freedom, right? You actively participate in the grid. And also the device on the left, that is called a phasor measurement unit. What that unit does is that unit is able to take very high time resolution data, so many hundreds of times per second. So now we have data that we never had before. And what does that imply for the system? So all this together, the new grid, or if you often hear the term smart grid, is really to say we have a grid that is driven by this intelligent endpoints. So this is quite a paradigm shift in the way we think of power system and we think of grid. So let me make this clear. Right? So traditionally, how do we design the grid? Traditionally, we always thought of the grid as a very top-down model. Right? So the grid fundamentally carries power from generators to loads. And traditionally, the first step is always let us understand the generators. Right? For example, you have coal, you have gas, you have hydro, you have many other kind of generators. And we have very detailed understanding of the generators. We have very detailed models. We know exactly how they work. So before, a lot of effort is spent understanding these generators. Now the next step is to understand the system in between, to understand the grid. And still, we spend a lot of time modeling this grid. How do we transfer power? How to control it? And the load, traditionally, has not been paid a lot of attention. Right? So how do we model load? How do we model the end consumers? We just think of them as an AC motor. So the detailed effort, you spend a lot of effort at the top, not much effort at the bottom. Right? So with this new design, this new paradigm, by looking at the end resources, the endpoints, we're going to shift this to a bottom-up design. So we'll spend a lot of time understand what load is. So it's no longer sufficient just to think of load as an AC motor. Right? So we really need to think of load as something with humans in the loop. You have end customers consuming energy. They have control of their own devices. And these devices turns out to be the control knobs for the system. So we'll try to understand the endpoints first. Then we'll go one level up. We'll go to the grid. We'll think of what does this mean for the grid. And then we'll think of how do we make generation. So where does generation fit? So we'll start from the bottom and go up. Right? So this is our design methodology, try to understand the endpoints of the grid. And so if you put everything in terms of a very high level view, what's going on here? So in the past century, what we have done is we have designed a pretty good system. of bringing power from generators to demand. Right? So the system is very capable of making sure supply exceeds demand when you have a generator. So this was accomplished. So this is a great accomplishment. But nowadays, we're changing the system. Or because of society's concern, right, for carbon, global warming, and for other things, we're adding things to this system. For example, renewables. By adding renewables, we're injecting a lot of randomness into the system. So our old way of designing systems is no longer adequate. Right? So we need to think of new ways to control it. And the good thing is we also have a lot more control knobs to tune. For example, demand response. So before, we always thought of demand as something fixed. Right? We change supply, we try to meet demand. But demand response is saying that demand is not a knob you can tune. It's not some fixed number anymore. And that is very useful. Also, another knob from the hardware side is power electronics. So by installing power electronics, we have many more degrees of freedom in the system that we can work with. So the challenge is that we're injecting new things. We're injecting randomness into the system, but we're also giving engineers new knobs to tune. And to really tune these knobs, it turns out we need to go back to the old system to understand the physics of the system better. And also, we want to close this loop. Right? So remember our design. So we want to close the loop. We want to go from bottom up. So we want to understand how does demand influence generator, and we want to design algorithms to close this loop. And it's also important not to only understand the physics of how power flows, but also understand how does people fit into this. So this is inherently sort of a cyber-physical system where humans are in the loop. And then data becomes very useful to us. Right? So together, by understanding the physics better, understand the people better, and using data, we can overcome the challenges of designing sort of the 21st century grid. So this is a broad overview. So then let me just go into a sort of specific problem to show how these things come up. So one sort of canonical problem, or a basic problem in power systems, is called voltage control, or voltage regulation. And that simply means, let's say you have a grid. Right? So this is a residential grid. Think of each of the nodes as a load, as a building, let's say. And you're trying to supply power from the left to right. And you look at the voltage. So think of the voltage as something you measure, just measuring from the wall socket. You want that to be around 120. So often, the voltage tends to drop as you go down the line. Right? But we want to keep it at 120, so we install a, so you can think of this being a capacitor there to pull the voltage up. And this is how the grid works today. And this capacitor works well. But these capacitors are mechanical switches. So their switching lifetime is limited. So right now, we switch them a few hours or a few times, 1 or 2 times per day, right, to keep the voltage constant. But with renewables, this mechanical device no longer suffices. So let me show you why. What happens when you add renewables? Right, so this is the profile we want. What if you're adding solar? Well, if you're adding solar, the voltage tends to rise pretty dramatically. And I cannot use my old capacitor to do voltage control. Because think of how fast does solar vary. Right? So if you have a cloud over an area, solar varies from minute to minute or second to second basis. And your own mechanical switch that cannot switch that fast. Right? So we have to deal with this sort of, this is what we mean by new resources coming to the grid, and this presents a big challenge. And you do see this in practice. If you go to San Diego, they have this problem. You go to Germany, they also have this problem. So solar tends to cause very large voltage deviations. Conversely, if you look at electric vehicles, they cause voltage to drop, also quite dramatically. But they also change on a very fast basis. So you still cannot use mechanical switches to correct for voltage. Right? So, but for the system to work, we have to keep the voltage flat as some reference. So how do we do that? Right? So we have these new resources that we want in the system, but they cause a lot of problems in the system. So one of our new control knobs coming to rescue, and these are the power electronics on the devices themselves. So these power electronics not only does power conversion, it also injects reactive power. So this reactive power is able to keep the voltage at this reference. Not only that, they can actually save us a lot of money. Right? So if we really optimize over how to use this power electronics, just by saving in thermal loss, so this just by keeping the thermal loss in the network down, this can mean billions of dollars of savings in the US per year. So there's quite a lot of opportunity in using this power electronics to do control. So mathematically, you can always formulate this into some optimization problem. For example, we can write the problem like this, where the operational constraints will include the system constraints. Right? Remember from before, we said we want flat voltage. So flat voltage is a constraint. We want reactive power. Reactive power and active power constraints model the capability of the devices. And the Kirchhoff's and Ohm's law, those are the physical laws that govern power flow. And your objective function, as we said, can be simply as a thermal loss or some other objective function. So this, we can write down this constraint optimization problem, and this tells us how should we optimally control our new devices in the grid. Okay? And this problem is not new. Right? So this problem has a very good name. It's called the optimal power flow problem. So it says optimally, let me decide how does power flow in the network, and this is the basic resource allocation problem. And this problem has been looked at. So I'm definitely not the first one to look at this problem. This is a very old problem, has been around since the 1960s. So it is known, after about 50-some years, we know it is very hard. We know it is not convex. But this is the optimization problem that we want to solve to control these new devices. So the challenge is that this thing is non-convex. A linearization, so you cannot really linearize this problem. It's highly nonlinear. So linearization does very poorly here. And the scale tends to be very, very large. So the scale, imagine everybody owns a solar or have an electric vehicle or has a small thermostat. Easily, the scale of this problem can go to hundreds of thousands of devices, of variables. So this is a challenging problem. But the good news is that we are able to solve it. So it turns out, even though the problem on top is very challenging, there is an exact convex relaxation for this problem. So for the people in the audience who haven't taken convex programming before, you can think of this as the problem is not convex. You put it into the computer. One, the computer may not solve it. Second, may not be optimal. But if we can show the problem is convex, you put it into a computer, you're guaranteed a global optimal solution in polynomial time. So convexity is a very powerful result here. Right? And this, we have been able to show it. So this is a known result. And this happened in the past sort of 3 or 4 years. Through a lot of effort, we show this problem is convex. So I won't go through the proof here, but I just want to contrast what's going on. So if you look at the old transmission network, right, so this is the high voltage transmission network. This power flow in this network is non-convex, it's hard. If you look at the distribution network, because the network has a tree topology, even though the problem, if you write it down, is not convex, we can show an exact convex relaxation. So why do we get interested in this network here? Right? Think about all the new devices. They're all coming in the distribution side. So distribution means the low voltage connecting to the end customers, to the households, and to the end buildings. So before, nobody cared what went on in this network. It wasn't important. We just thought everything as an AC motor, power will just flow. But nowadays, because we have all these new devices, optimization in this distribution network became very important. And turns out, because of the tree structure, we're able to solve it. Right? So this is a quite sort of, this is considered a major breakthrough in the field. To show this is, we have a convex relaxation here. So what does convex relaxation? So first of all, the good thing convex relaxation gives you is that we have a polynomial time solution. You put it into a computer, it's not hard to solve. But also tells me much more, right? So because we understand the problem is convex, it gives you a decentralized algorithm. For example, let's say you have a network like this. So normally, how you solve this kind of problem is you connect all the data together to some central location, you run your optimization problem, and you solve it. But it's not necessary to do that. It turns out it's sufficient just for nodes or buses to exchange information on their own. So here it shows that only pairs of buses need to change so they need to exchange lambdas. And by exchanging these lambdas, you can show we have a decentralized optimal solution for this network, for this kind of problem. So this is one good result from the convexity. And also, we can actually design a market, or we can understand the economics in this grid. So let's suppose to say I want to run something like demand response. How would I model demand response in this context? Well, look at the cost function. So think of this cost function is a cost function faced by the system. And in demand response, the system may face a very high cost function. So then the system goes to individual users, which is the utilities. And each of users, let's say you have a utility, representing how much do you want power, right? How much do you want your electric vehicle to be charged right now? If you have a utility function, and the system has a cost function, you can actually, so this problem, since we show it's convex, you can solve it. And furthermore, this lambdas, multipliers, can be interpreted as prices in the system. Right? And this prices has economic meaning. These are the prices you would actually charge the end users. And they are, in some sense, the best price you can charge, the correct price you should charge. So let's take a breath and look at this result. This is actually quite a powerful result, right? By knowing the problem is convex, we have a decentralized algorithm, and we have a market set up. So this is good. So if I take this, so let me go to I'm going to practice, go to a company, go to one utility, and say, can you run this algorithm? Right? I have a very nice algorithm, please run it. They will tell you, actually, you cannot implement this in practice right now. Why is that? Because of two fundamental challenges we have to address going forward. The first is communication. So we always thought of smart grid as a power grid with some communication network on top of this power grid. Right? So the physical power will flow in the power grid, and the information exchange will happen in the communication network. But in practice, if you look at residential networks, this communication network is not there. Very, very few utilities in the world have a real-time communication network there. So even though our decentralized algorithm only requires information exchange between two neighboring buses, we still cannot do it. There's no information exchange right now in the network. Okay, so first of all, we don't always have communication. Right now, we actually have very little communication. And second is, do we really want communication? Right? If you build a system that's very reliant on having sort of real-time, reliable communication, the system is quite vulnerable, right? Quite fragile. But power grid is something inherently we want to be robust. So the question is, so communication is one fundamental question. Do we have it, and do we want it? The second is really about understanding customers. So we said we should not model them as AC motor, right? Humans don't behave like AC motors. But we replace this model by a utility function. So I will argue humans don't really also behave like utility functions, right? We don't wake up, the first day we do is not to say, okay, I'll get some increasing concave function as my utility with respect to power prices. Right? We don't do that. We don't know. We don't have a. We may or may not have a utility function, but we certainly do not sit down and spend time drawing this utility function and giving this to the system. So this is the question. Right? So to make this power system work, we really need to address, one, what happens with communication, and second, what happens to this utility function? How do I model people in this system? So the rest of the talk will tackle these two questions. So first, let us look at communication. What happens with communication? So California, if you look at California, we have about 200,000 solar. So 200,000 rooftops have solar. And they send data once per day. Right? So this is very not real time. So this data is just for meter reading only. But as we showed before, when you have a lot of solar in the system, you have to act. Right? To make the voltage stable, you have to constantly adjust your output. Then so because we have no communication, each of them must act based on their own local information. Okay, so let's see what happens when we only use local information. What kind of control we can do. Right? So again, so this is our system. VIref is some reference voltage. And we have active and reactive powers, P and Q. So the active power, the P's, you can think of them being set externally. As a they're based on, so you have a solar panel based on the solar irradiation, based on the cloud cover, you have your active powers. That will not change. Your reactive power, the Q, this you get to control. Right? So our goal is to say each device will control your reactive power, will control Q to keep V via reference, as some reference voltage. And the algorithm actually turns out to be quite simple. So the algorithm is just at any time t, you measure your own voltage. And based on your own voltage, if you say your voltage is too low, inject some power. If it's too high, take some power out. So this is a very simple algorithm. And we're trying to understand how well does this simple algorithm do. Okay. So if you write everything in terms of matrices, this is our update rule. So since we don't have any communication, the update is really a diagonal matrix. So you can only update based on your own information. And our goal is to design this D. D is a gain matrix. We want to design the gain matrix to make this entire system converge. Okay? And we have no real-time communication. So it's not enough to design a D that works for one active power. We really need to design one gain that works for a set of powers. For example, at the beginning of the day, I'll design a gain matrix. And this matrix, this D, must work for the entire rest of the day. So we're asking a lot here. Asking a controller with no communication, and that must work for a set of conditions. So let's look at stability. Right? So I run this controller. Does it converge or not? So we can try this out in a IEEE 34 bus network. If you try it out in this network, everything is very nice. So the vertical axis plots the voltage, and after some time, all the voltage converge to very nice number 1. So this is a network under normal loading. Then you ask, what if I increase the load in this network? What happens? Well, if you increase the load, actually the voltage diverge. Right? You see these huge oscillations in the network. And you may think, okay, you just design a bad controller. Let me design a better controller to make the graph on the left converge. It turns out there is no D that makes it stable. So for the situation on the left, local control is inherently unstable. No matter what controller you use, you cannot make the system on the left converge. So let's think of why is that. Well, so if you look at this system, in block diagram terms, this is just a feedback system, where Q is your input. P, you can think of some randomness into the system. You measure the voltage, and you subtract against the reference, you feed it back. And so this is just this is a system, and the problem, the mapping from Q to V is quite nonlinear. So this mapping is very hard to get a handle of. So how do we get a handle of the mapping? So normally, we think of given voltage, we try to get power. And this is straightforward. So going forward in this direction is quite easy. Coming back, solving this inverse problem is no longer easy. Right? So for control, we really want to solve the inverse problem. I want to say, how do I control Q to make a V stable? And this is hard. So of course, given any PQ, you can numerically calculate. Okay? But as we said, we want to make sure our controller works for a range of active power. So we really need to get some analytical solution to this. And the trick, after you spend some time with it, actually there's a simple trick makes this easy, is you don't look at voltage, look at voltage squared. So do this change of variable. Actually makes your life much easier. So if you do that, change of variable, actually you can now take a Taylor expansion. And this Taylor expansion is much easier to do. So it breaks off into two terms. First term is linear in Q. And so this term is 1 over reference to the cube, so that's a small term. So what's the first term? So this first matrix actually also decomposes into two terms. The first term depending on the topology of the network, where the second term depends on the active power of the network. So the first term is always positive semi-definite. The second term is not. So this tells us when the power is small, only topology matters. And topology tells you it's positive semi-definite, so your algorithm, your logo update will converge. As your power increases, as your power changes around, the second term starts to dominate. And this entire matrix is not PSD anymore, so your local algorithm may not converge. So the result is the following. So think of the injection region. So at the beginning of the day, let's say your power is bounded by some upper and lower bound, whereas the lower PI lower bound is a maximum demand. Okay? And we can show a result which says it suffices to design a D that is stable for so look at this lower bound only. Design a controller for that. You're guaranteed the controller will work for all power in that set. So this statement says you don't have to check all of them. Just check one of them, and this controller works for the entire region, for every power in that region. Why is that? Well, it turns out convexity from before actually matters here. So even though we said so showing the problem is convex actually gives us a lot more than just a polynomial time solution. It really means that we understood the problem well. We understood sort of the geometry of the problem. But understand this geometry of the problem also allows us to show sort of very strong result like this, which means designing, just check one number, you can design for the entire region. Now you ask the converse question, are there fundamental limitations to this? Can I always design diagonal control? And of course not. Sometimes if the load is too heavy in the network, there's no diagonal D that will make this system controllable. And this depends on the topology. So compare these two networks. You have a star network on the right and the line network on the left. The line network is harder to control. Actually, there's an interesting limiting result you can show here. You can show that as the network gets longer and longer, it turns out I cannot control this network for any positive demand. So as the network gets longer and longer, it becomes very harder and harder to control. As it gets very long, it's impossible to do control in this network. So this shows us without communication, you run into some fundamental limitations. There are some networks that's very hard to do control with. Now we can come back to communication. Let's think of, suppose I don't require sort of real-time communication between all the buses. I only require some communication. Let's say I only give it a very long network. I allow you to build one communication link. What happens in this network? So where do you put the communication link in this network? So it turns out the best place to place this communication link is in the middle of the network. So you place communication in the middle, means the two middle nodes can exchange information. Nobody else can exchange information. Actually, and this helps actually quite a bit. Right? So there's a 3-step algorithm where you say this communication link, you can think of it breaking up this network into 2 parts. So you do your local update on the first part of the network. Then you come back to your update in the second part. Then you do this update in the first part again. The result of having one communication link actually breaks up this network into 2 shorter networks. So if the local algorithm works on the shorter networks, but adding one communication link will work on the longer network. So communication helps a lot. Even limited communication helps quite a bit in designing these networks. So if you take a look at this network, all the nodes are the households, are buildings. But we said in the beginning of the talk, we want to go deeper. We want to understand the sort of the end resources. So let us look inside a house, inside a node. So right now, if say you have a home, and you have this new fancy devices, solar, electric vehicle storage, and so on, actually there's a lot of conversion going on in your home. Because solar, electric vehicle storage, these are all DC devices. You have a solar panel, will generate a constant DC voltage. But for your other appliance in your home to use this, you have to convert this to AC voltage, a sinusoid. Right? But nowadays, more and more of the loads in our homes are actually DC load. LED lighting is DC load. Your computer is DC load. Your cell phone is DC load. So for them, we have to do a double conversion stage. Right? You have to go from AC to DC again for those loads to use it. So there's quite a lot of double conversion going on here. And also, another problem for the network is that any variation in any one of these devices immediately shows up on the grid. Right? So let's say you have a solar and electric vehicle. Something changed in your solar. Immediately, because you do DC to AC conversion, this shows up on the main AC grid. But there's actually a lot of opportunity for you to just balance this out in-house. In home, you already have a lot of devices. Why not balance this in your home without making everything show up in the main grid? So one possible design is to change everything to a DC-based. Right? So let's say you have a DC line. Oh, sorry, those blocks should be, this should be DC-DC convergence. There should be DC-DC convergence. And you do everything in terms of DC. And this is potentially much more efficient, and this allows you to do in-house balancing. Right? You balance everything in your DC network first, then you put it onto the grid. It's much better for the grid in that way. So again, these should be sort of DC-DC convergent blocks, not DC-AC. So if you look at DC-DC converters, they're actually not that difficult to design. So here I'm showing a buck converter. And this converter just steps down the voltage. Right? So you have some voltage on the left end, you're driving a load on the, so you have some voltage on the right end, you're driving a load, and this thing just steps down the voltage for you. And this is open loop unstable. This is known. So you need some feedback control. Right? So you use your duty cycle, dt, as feedback control. And so you feedback the voltage measurement at your load, and you feedback this to the duty cycle, use this as control. And this has been tuned very well. So whenever you buy a DC converter from the store, they will tune this for you. They have a controller internal to it, they'll tune it. Now the question is, what happens when we connect a bunch of them in a network? Right? So we're interested in building a network of these devices. So let's say, let me put back 2 of them back to back together. And it's very easy for this network to go unstable. So even though you tune individual ones very well, the network actually can go unstable. So again, we're going back to our question is, I want to design robust gains. Given the topology, I really want to design gains where this network is stable for a wide range of loads. And really the best thing you can have is actually plug-and-play capabilities. So you want to say, no matter what I put into this network, if I can change the topology however I want, I still want to be stable. So this is called plug-and-play. And we're trying to, so we made some progress here, but there's a lot more work to be done here also. Okay. And in here, communication is really, really hard because all these converters switch at a very high frequency, about 10 kilohertz or 100 kilohertz. So really cannot communicate the states back and forth. And you have to think of a lot, so there's a lot of joint design between the controller and the power electronic device themselves to make this kind of system work. And also, let me go into a higher level of how we design the power system. So remember our first few slides, where we said power system is driven from a top-down point of view. That is correct. In the past, a lot of the work is done by looking at what happens when you have machines. The power system, in the past, is governed by Newton's second law of these machines. And you really cannot do much about that. I mean, there are the physical laws. But you look at power electronics, these electronics has no inherent physical laws that govern with them. You can use them however you want. You can implement any digital control that you want. And this has a lot of potential design opportunities. This really gives us a lot of freedom of thinking how we design the problem, how we design it. And this is where you have to jointly think of the problem. Not only to say, how do I design a best one converter, but when you design it, you have to think of, if I put them in a network, how would I use them? Okay, so this is how does power electron. I think there's a lot of potential in this kind of thinking here. Okay? So then let me go back to the problem to say, should we communicate or not? So the system that doesn't rely on communication is quite robust, actually, because not much can go wrong. So how would you attack a system that doesn't rely on communication? So this was one of the attacks that look like. So this attack actually happened. So this is the map of San Jose. So this is San Jose, and that's a transformer. So how will you attack this power system? This is what happened. So in about 2 years ago, at 2 a.m. in the middle of the night, someone took a rifle and shot at it. Right? Then they fired about 120 rounds into it. And these people are pretty smart. So they only fired at the transformers that were on. So we're not sure, we're still this day not sure how they determine which one is on. But they managed to fire at the ones that were on. And this caused a lot of cooling oil to be leaked. So the transformer tripped, basically. It shut down, so this part of the grid was shut down. And these people were smart enough to cut the fiber optics and phone cables, so no one can actually call. So the police didn't know this until next day. So this is a quite sophisticated attack. Okay? But this also shows you right now, to attack the power system, it requires a lot of work. You have to know where it is. You have to go out in the middle of the night, get a military-grade rifle and shoot at it, and then physically cut the communication system. So that's why this only happens once or 10 years or so. It's just very hard to do. Right? So someone in another country cannot do this for you. But if you build a system that's very reliable on communication, you don't need to go through all that trouble. You don't need to take a gun and shoot at it. If I build a system that's very reliable on communication, it's very fragile. It's much easier for me to hack a communication system, right? For me to hack the system that's based on data exchange and shoot at a transformer. So the system, even though communication is extremely helpful, as we saw before, one communication link can dramatically improve your stability, but also makes the system much more vulnerable. And the idea is to say, we need to understand the trade-offs. So smart grid, I think, is not naively just to say, when you have a power system, let me put in as much communication as you want. I think you really have to think about it, when to use it, and then understand the trade-off of adding communication. Okay, why does it help? So this will wrap up sort of the physical part of the talk. This is how the physical system works. So let us switch gears and let us look at customers. So what happens, right? So let us think of what happens when humans are in the loop. So again, customers, these are really not passive devices. And they're also not utility functions. Right? So it's very hard for me to come up with my own utility function for energy. I imagine it's also hard for other people too. Right? We really don't think of energy in that term. We don't think of it as a utility function. Okay? And with all the technologies that's coming into our lives, it's actually making this problem worse for us. So engaging with customer, in some sense, is getting easier because all the internet technology. In other sense, it's also become very much harder. So technology do influence customers. And then you start seeing this kind of news report, right? So there's a newspaper that says automatic bill payment programs cost money, increase consumption. Right? So this is, you don't look at your bill every month now. You sign up online, it will automatically deduct money from that account. This actually is bad for the grid. Your consumption goes up. So this is a big study done by Sexton, and this just published to say, if you don't make people look at their bill, they'll consume more because they don't care anymore. Okay? So how do we solve this problem? Well, one way is to take a bill to them and force them to read it. But that's not very practical. So if you really think about how does customer interact with the grid, they actually interact quite a lot. Right? Suppose you have a smart home. It's very easy nowadays to input a command. Let's say, do my laundry while I'm asleep. You tell this to your smart home will schedule appliances. Very easy. So it's getting easier and easier for customers to ask for things. But then there's a mismatch between the grid and the customer. If you're a system, you're really trying to solve this problem. Right? I have a physical system to run. I have physical constraints I need to satisfy. And to allocate how much power to each customer, I need to solve this optimization problem. The customers just have a big list of things. It says, do my laundry, charge my car, keep my temperature correct. So how do we translate from what customer want to the problem in the grid? How do we learn their utility functions? And this is not just simply a problem. Right? So right now, we actually let customers do whatever they want. Right now, you say you want to do your laundry now, fine. You want to charge your car, it will happen. But it's not, if everybody has an electric vehicle, it's not possible to charge them at the same time. So we really need to figure out their utilities, who to allocate this resource to. That's all right. So we need to do some translation. And it's not simply a matter of translating, say, English language to math. It's actually more fundamental to that. So the user utilities, the system doesn't know user utilities. The user themselves don't know their utilities. Right? You are not aware of, so we are not able to draw our own utility function right now. So both of them do not know. So the system is so this learning process, this discovery process, is much intertwined between the system and the utility. So between the humans and the physical system. And also, this is a dynamic process. People's utilities change over time. So it's not possible to say, tell the people, fill out a very detailed survey, I'll learn utility. That doesn't work in practice. Right? So you really need to dynamically discover people's utilities. Right? So you have to keep doing this across time. So this is where this is an interesting case of cyber-physical systems. Normally, when we design cyber-physical systems, we separate the human and the physical system. Right? When we design a system, assuming humans will act as rational agents, and we try to understand users by sort of thinking the system operation as given. That's no longer adequate here. So both of them must go together, this discovery process. So the system and humans are really intertwining a learning loop. Right? So the system can send out price signals to users, and users they will respond. For example, I say your price is double right now. I'll look at, do you still charge your electric vehicle? Do you still do laundry? Or do you delay those? From your response, I'll learn something about the users. But the users is also learning something about themselves. So you have two learning loops that are intertwined together. And we need to capture this idea of how they learn at the same time, how you learn at the same time. And so normally when you think about learning, you think about big data, right? Nowadays, it's very popular to say, given a lot of data, what can we learn? Here, it's really a case of small data. You cannot send too many messages to a user, right? So it's maybe fine for a customer to get, say, one text message a month. It's not OK to say give this text message to a user once every hour. So we only have a few opportunities to send out price signals. And we want to sort of get the maximum bang for the buck of learning here. So sending a signal is very costly. How to maximize efficiency? So this is a simple model for it. Let's think of users coming in as xi, as some covariant variable. And you make a decision. You can either treat them, you can either observe their outcome, or you can let them go. So this in power, you can think of this as, I send them a text message, I observe the outcome, or I don't do anything to them. And you only treat a few users. Okay? So let's take the simplest case here. Let's say everything is linear regression problem. And you have a linear problem, and you want to learn beta, right? Your goal is to learn this coefficient beta, but where you have n data points, you have n users arriving in this queue, you cannot use all of them. I only allow you to pick k of them. How will you optimally pick this? And one sort of the standard method right now is pick randomly. And we know how this scales. So your error basically scales, the square of your error goes down as 1 over k. But so what happens if you strategically pick them? Say if you don't pick the first k users, what happens? Well, if you strategically choose, you can have a gain here. You can get a gain of log n in here. So you learn better. The error goes down faster. And this log term actually matters quite a bit in practice. So this problem is also an example of intersections. Right? So this problem actually came out of a discussion with some companies that were trying to sell ads online. In their sense, they also have this problem. You have many, many users coming in. You cannot really follow up on some of them. Right? For a company to follow up on a user, you need to call them, you need to send them mails, it costs a lot. So you can only sort of observe a few fraction of them. And in both cases, this n, the number of users you have, is much, much larger than the number of treatment you can do. So this log n really matters here. So this term really matters. They can learn much, much faster if you actively pick people. Okay. And this is only in dimension 2. So right now, we're working on higher dimensional case. And turns out in higher dimensional, this will matter even more. So you have to actively pick and choose. From a system point of view, you have to actively probe the users and not just wait until something happens and send a signal. You have to learn this by sort of picking the best signals, picking the best cases to learn the user from. And this makes the problem much easier. So this is a difficult problem, but we think, good. Okay, we have a gain here. So then the question we should always ask, why do we care about individuals? Why should we learn about individuals? It's much easier to learn the aggregate response. If I pull together 10,000 people, if I send a signal, the average behavior is much easier to learn. Why do we need to go through all this fancy math to learn individual behaviors? And then you need to connect this back to our physical problem. Think about it. The first part of the talk is about voltage regulation. And voltage is really a local phenomenon. If this user changes something at the end, so if the user at the end of the grid does something, will cause a local voltage phenomenon. And telling everybody to reduce their consumption is not the best way to solve this. Actually, may not solve the problem. In this case, you really need to target the individual users. Also, if you do something like demand response, you want to figure out who contributes to your demand response. You don't want to say this aggregate reduced by 10%. You'll pay everybody this money evenly divided. That's not the best way to do this. You want to figure out who contributed more, who is actually who is doing this demand response for you. So in all these cases, it's very important to learn about individuals. So to conclude, I want to say that the power system is changing quite dramatically. Right? It's going from a very top-down system to a bottom-up system. There's a lot of opportunities to do fundamental work. But the good thing about this is we may actually see some of this work implemented in the next 10 to 15 years. So this is a quite exciting field for me. And the thing we understood from the sort of in the last 3 or 4 years, we really figured out how does resource allocation work in tree networks. But there's a lot of open problems. For example, you give me a network with cycles, this is still quite open. How do I do resource allocation in a network with cycles? We don't know. And we need to understand the trade-off between communication and control. And namely, how do we leverage this sort of very high time resolution measurement, this high time resolution data? How do we use them to control the system better? And we need to worry about what happens when humans are in the loop. And we need to jointly design power electronics and power systems. And this concludes my talk. Thanks.
Thank you, Baosen. Any question to Baosen? Please.
Yes, it looks like you like have some stability issues, especially when things are far apart and clusters. One gets low, another gets. You understand how to deal with that?
Right. So the question is, if you have a large network, so one part may have a problem, the other part may not. Right? You have stability in localized parts. And this is where sort of the local control comes in. Right? If you have a problem, change your own behavior using your own resources. And also from a system point of view, that's why we need to care about individual learning. We need to really target people as the problem areas better.
A question about the data used for this. Like, how much data is available and what types of data are available for these sort of power system optimization algorithms?
Right, so the question about data, how much data is out there? So if you want to do optimization of power systems, there's quite a bit of data out there. So that has been done for the last 50 years. So it's not hard to find data. And even for this PMU measurements, there's some data online. So it's not that hard to find data in that case. If you want to do customer engagement, then privacy is a problem. So companies tend to be quite hesitant to share their individual data with you. But it's getting better. So in a sense, there are open database online that contains customer data you can look at, and you can certainly work around companies to get their data. And also, this is a technical question: is how do you sort of hide the privacy information from the data? Right? If you're able to take the data and process it in a form that's still useful to you to do research, but where you cannot tell about people's private information, there's some research going on there too. So that's an interesting question with data. Questions?
Any other question to Baosen? Okay, if not, let's thank the speaker again.